1,000 years. In the pursuit of developing clean energy technologies, we might end up producing waste that might have to be stored away vegetation and water sources for over 1,000 years. And I'm not even talking about spent fuel or contamination. I am talking about structural parts, the walls, the handling tools, so on and so forth, that are made of steels and cast irons that are inherently not active when they are commissioned, but they acquire radioactivity or they acquire activity due to the constant presence in the vicinity of nuclear transmutations. This phenomena is called acquired activity. Think of it like a piece of iron becoming a magnet in the presence of a strong permanent magnet. This is actually worse compared to polymers and plastics that are traditionally considered to be polluting materials because you cannot incinerate iron even under controlled conditions. I am here to share a breakthrough with this group that the induced activity can be brought down to less than 100 years, and I have figured out a way how. When we look at the periodic table of elements, we can easily identify the elements that have reduced activation properties, properties that can withstand high temperature, high corrosion resistance, exceptional strength, toughness, yada, 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 all the nice engineering properties, and elements for structural alloys. Now, this selection of elements is known to scientists for several decades now. So, where is the knowledge grab? Why are we not making materials that have low activation time? The problem is alloy development. You see, traditionally, if I take the example of steel or aluminum alloys, we have a base material like iron and other alloying elements added to it. My approach is radically different. It is using the concept of high entropy alloys, where we mix equal or nearly equal proportions of multiple elements to stabilize a phase and alloy. And the consequence of this is the alloy design space is extremely expanded, over 1 million compositions. I have developed not one, not two, but 6 alloy systems in commercial scale, and also have tested and found that these are not only strong, tough, and also have a hands-on time of less than 100 years. As shown in the TM electron micrograph here, they also self-heal themselves, going from crystalline to amorphous, and from amorphous back to crystalline upon heating. In conclusion, these alloys have very high damage tolerance, exceptionally low decay time, and also display self-healing properties, opening up the space for SMR, fusion, hydrogen storage, not just terrestrial, we are going into space and cryogenics. Thank you.